Bismillahirrahmanirrahim. Assalamualaikum, students and friends. For a change, our episode today focuses on a particular concept in chemistry, the colligative properties of solutions, boiling point elevation, and freezing point depression. So just stick around till the end of this video. Watch and learn. The problems are: number one, calculate the boiling point of a 2.50% solution by mass of sodium chloride in water. Question number two. During winter, sodium chloride or calcium chloride is often sprinkled on icy roads to melt the ice and make driving safer. The solubilities of sodium chloride and calcium chloride are about 36.0 grams and 60.0 grams, respectively. Per 100 point grams of water at 0 degrees Celsius and 1 atmosphere. Calculate the freezing points of both solutions to see which salt is more effective at melting ice. So first thing first, we are given the percentage concentration by mass of sodium chloride, which is 2.50% solution by mass of sodium chloride dissolved in water. The boiling point elevation constant for the solvent water, denoted by capital K sub B, is also given here, equal to 0.512 Celsius degree per molal. Likewise, we are also given the mass of the solute, right? Equal to 2.50 grams of sodium chloride. And the mass of the solvent equal to 97.5 grams water. For question number 2, we are given the solubility of sodium chloride, okay, equal to 36.0 grams per 100 point grams of water. For calcium chloride, its solubility is 60.0 grams per 100 grams of water. The freezing point depression constant for water, denoted by capital K sub F, is also given, equal to 1.86 Celsius degree per molal. So moving on to our computations in question number 1, we first compute the delta capital T sub B, or we call that the change in the boiling point of the sodium chloride solution, using the formula or the equation delta capital T sub B equals the product of I uh, K sub B and the molality small m, where small letter I is what we call the Van Hofer factor. It represents the number of ions a solute dissociates into when dissolved in the solvent, impacting colligative properties. So, notice that in the formula or equation for determining the change in the boiling point of a solution, or delta capital T sub B, right? Uh, the amount of the change in the boiling point is directly proportional to the molality of the solution. So, we have to determine the molality, right, of uh, the given solution or the sodium chloride solution by first finding the uh, amount of uh, moles of the solute, all right, which is simply dividing the given amount of mass of the solute, that is 2.50 grams, by what we call the molar mass of the solute. And in the case of sodium chloride, its molar mass equals 58.4 grams per mole. So when you do our math, we find the mole solute, or the amount of moles of the solute sodium chloride, equal to 0.0430 moles. We can now determine the molality of the sodium chloride solution using the definition of molality, right? So small letter m represents the molality, which is simply the amount of, or the number of moles of the solute divided by the mass of the solvent expressed in kilogram. So in the case of the molality of the sodium chloride solution, right, uh, we have the number of moles of the solute computed earlier, 0.0430 moles, and then divided by the mass of the solvent, water, expressed in kilogram, 0.0975 kilogram. So when you do our math, we find the molality of the sodium chloride solution, small letter m, equal to 0.440 molals, right? So the unit small letter m, okay, means molals, which is the same as moles per kilogram. So that brings us to our computation for delta capital T sub B, or the change in the boiling point of the sodium chloride solution, using the formula delta capital T sub B equals the product of the Van Hoff factor or index small letter I multiplied by the constant capital K sub B, right? Or the boiling elevation constant for the solvent water, of course multiplied by the molality of the sodium chloride solution. That is, delta capital T sub B equals 2. 2 here represents the index, all right, of the Van Hoff factor for the solute sodium chloride, right? So when sodium chloride, which is an ionic salt compound, is dissolved in water, it dissociates into two ions, right? One positive sodium ion and one negative chloride ions. That's why uh, I here has a value of 2. Then the value of capital K sub B of the solvent water is 0.512 Celsius degree per molal multiplied by the computed molality of the sodium chloride solution, 0.440 molals. So when you do our math, we find the value of delta capital T sub B of the sodium chloride solution equal to 0.450 Celsius degree in 3 significant figures. So that means the actual uh, boiling point of the sodium chloride solution, in other words, uh, the elevated boiling point of the solvent pure water, okay, with an amount of sodium chloride dissolved in it, okay, will just be the sum of uh, the normal boiling point of pure water at STP, which is 100.000 degrees Celsius, plus, of course, the value of our computed delta T sub B, 0.450 Celsius degree. Or that will give us the value of the actual elevated boiling point of the solution sodium chloride equal to 100.450 degrees Celsius. In question number 2, we first determine the molality of each of the salt solutions. So for the sodium chloride solution, the molality equals 36.0 grams per 100 grams. This is the given solubility of sodium chloride, which means 36.0 grams of the solute sodium chloride will dissolve in 100 grams of the solvent water. Then we multiply it by uh, the what we call equivalent of 1 mole of sodium chloride, which is 58.4 grams. And of course, multiply it also by the conversion equivalent of 1 kilogram, which is 1,000 grams. Okay? So when we cancel the unit, all right, we'll come up with the molality of the sodium chloride solution equal to 6.20 moles per kilogram. Also in 3 significant figures. And of course, for the calcium chloride solution, the molality is also determined by uh, using the given solubility of calcium chloride, that is 60.0 grams per 100 grams of water, right? And then multiply it by the equivalent of 1 mole of calcium chloride. The mass equivalent is 111 grams. And of course, the gram equivalent of uh, 1 kilogram. So again, canceling the units will also get the molality of the calcium chloride solution equal to 5.40 moles per kilogram. Moles per kilogram here can also be called molals, right? So you will notice that in terms of molality, right, the molality of the sodium chloride solution is greater compared to that of the calcium chloride uh, solution. And take note, right, these solutions use the same solvent, right, which is uh, an amount of uh, water equivalent to 100 grams, right, or 0.100 kilogram. Finally, we can now determine the delta capital T sub F of the sodium chloride solution using this same formula, right? Delta T sub F equals the product of I and capital K sub F, and the molality is small letter m. That is, delta T sub F of sodium chloride equals 2 multiplied by 1.86 Celsius degree per mole. This is the constant uh, freezing point depression constant for the solvent water. And of course, the computed molality of the sodium chloride solution, 6.20 moles. So when you do our math, we find the change in the freezing point of the sodium chloride solution. Delta capital T sub F equals 23.0 Celsius degree in 3 significant figures. So that means the actual freezing point of the sodium chloride solution, which is just uh, the freezing point of pure water at STP 0.0 degrees Celsius minus our computed delta TF 23.0 Celsius degree. So that is equivalent to negative 23.0 degrees Celsius rounded to 3 significant figures. This is the actual freezing point of the sodium chloride solution. Likewise, for the calcium chloride solution, the delta capital TF using the same formula, I times capital K sub F times the molarity small letter m, right? So that is equal to 3, which is the value of the index of Van Hoff factor for uh, the calcium chloride solute. All right. Calcium chloride, when dissolved in water, all right, will dissociate into 3 ions. All right. One positive 2 calcium ion and 2 negative chloride ions. For a total of 3, right? 1.86 Celsius degree per molar, of course, is the freezing point elevation, depression. Okay, freezing point depression constant of water. And of course, the computed molality for calcium chloride obtained earlier equal to 5.40 molars. So when you do our math, we get the value of delta capital T sub F of calcium chloride equal to 30.0 Celsius degree rounded to 3 significant figures. So this means that the actual freezing point of the calcium chloride solution, right, which is just equal to 0.0 degrees Celsius, that is the freezing point of pure water at STP, right, minus uh, the computed delta TF for calcium chloride solution, 30.0 Celsius degree. So we get the actual freezing point of the calcium chloride solution equal to negative 30.0 degrees Celsius, also rounded to 3 significant figures. Right? So, uh, when we compare the actual freezing point temperature of the two solutions, the sodium chloride and the calcium chloride solutions, it appears that that of the calcium chloride solution is much lower, right, compared to that of sodium chloride solution. Therefore, we say that calcium chloride is more effective than sodium chloride at melting the ice. And this is primarily because of the greater value of the index, all right, small letter I, the index of Van Hoff factor, okay, greater in the case of calcium chloride as compared to that of sodium chloride, right? The higher value of I, in other words, the more ions being dissociated, okay, in the solvent water makes its actual freezing point much lower, right? And that explains why calcium chloride is more commonly used also on icy roads in most uh, countries that experience winter, right? Because it is more effective in melting ice compared to sodium chloride. Notice that the same solvent is used here, right? Water for both solutions. And you will notice that um, the number of moles of calcium chloride, right? Or the molality, I should say. The molality of the calcium chloride solution, in fact, is even lower compared to the molality of the sodium chloride solution. Okay? But why is the freezing point, actual freezing point of calcium chloride is much lower? Okay? Our conclusion is that it is because of the greater value for the index, all right, of the Van Hoff factor for the calcium chloride solution. So on this note, guys, ay mabuhay. Till the next episode, Mashallah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.